In this lesson we'll look at different ways of finding area. And in the previous lesson we found area by subtracting the top curve, subtracting the bottom curve from the top curve. So top minus bottom, this would be f minus g from 0 to 2. We have to pay attention to whether we're using a vertical rectangle or horizontal rectangle. In this graph you could have used either, but we'll just stick to the vertical whenever we can. So today we're going to look at regions that have a different top curve. So here G is the top, but then over here F is the top. So we just have to make two integrals, and in both cases we'll use vertical rectangles. And the vertical rectangles have a thickness, a width of dx, so that x reminds us that we're looking for x intervals for the integrals. And here we'll go from -2 to 0, and top is f minus g. And then from 0 to 2, but now it'll be g minus f. And the other difference is in a region like this, where if we look at the top and the bottom this way, we have the top curve and the bottom curve being the same equation. And in this one, if we wanted to use a vertical rectangle, we would have to solve this equation for y, which gives us a positive or negative radical. And then we have the positive radical, the negative radical. So it's possible to use a vertical rectangle, but if we do, then we have to have two integrals, because we have top, bottom here, top and bottom, or the bottom curve is different over here. So instead of doing that, we could just use horizontal rectangles, and that's where we have a width of dy, the differential of y. So when we use a horizontal rectangle, we'll be using all the equations in terms of y. So in this problem, I didn't find the intersections, but we would find those intersections. Let's just call it a to b, and we would have to solve this for x. Y plus 8 over 2 equals x. Then we can just do one integral with y values with a y interval from a to b, and then we'll go right minus left dy. So in this problem, the right side is y plus 8 over 2. The left side is y squared. So that's one of the types of problems we'll be working on in this lesson. All right, we're graphing sine. Bounded by the x-axis and also bounded by 0, x equals 0, and 2 pi. So we want the whole region, this top part and the bottom part. And in this case, horizontal rectangles would be more difficult because it's touching the same curve. We always want to use vertical rectangles. If we have a choice, we'll use vertical. And going back to the steps, we have, we're going to use vertical rectangles. So that means we have a width of dx, and that means we need an x interval for integration. So the x interval here, top minus bottom, goes 0 to pi. But then we also have to have a different integral from pi to 2 pi. And that's just because the top curve is sine, and here the top curve is y equals 0. And then we can integrate from 0 to pi, top minus bottom, that's sine x minus 0. Then from pi to 2 pi, top minus bottom, that's 0 minus sine x. So the antiderivative of sine is negative cosine. The antiderivative of negative sine is cosine. And you just check. If you take the derivative of that, you'll get that. The derivative of this is going to be sine. So we can check those. Negative cosine of pi minus negative cosine of 0. Cosine of 2 pi minus cosine of pi. Cosine of pi is negative 1, negative negative 1. This is plus. Cosine of 0 is 1. Cosine of 2 pi is 1 minus negative 1. Cosine of pi is negative 1. So the area is 4. And I think that would be a little unexpected to have that integer value for the area. Alright, pause the video and try this one. Alright, we have cosine, x equals 0, x equals pi, and y equals 0. So we're going to find the area of that region. Step 1, do we want vertical or horizontal rectangles? Here, either one would work, but we'll just stick with vertical if we have a choice. So that means we're going to use dx, and that means we need an x interval. The x interval is 0 to pi over 2. And then from pi over 2 to pi. So we integrate from 0 to pi over 2, and we'll have top minus bottom. So the top is cosine. The bottom is 0. Now the top is 0 and the bottom is cosine. Cosine is the derivative of sine, so the antiderivative of cosine is sine. 0 to pi over 2. And here we'll have negative sine. Sine of pi over 2 minus sine of 0. Negative sine of pi minus negative sine pi over 2. Sine of pi over 2 is 1, sine of 0 is 0, and sine of pi is 0. Sine of pi over 2 is 1, and we have 2 for the area. And also, if you recognize that there's symmetry here, you could just find the integral, find the area of this, and then just multiply it by 2. But we were practicing setting up the integral with 2 intervals. Alright, so here we have a horizontal parabola, and this one is shifted to the left 2. Here it's reflected across the y-axis. And we want to check, should we use vertical or horizontal rectangles? If we use the vertical rectangle here, then we have to isolate y and get a positive or negative radical to identify the positive side and the negative side. So it's easier in this problem to use a horizontal rectangle. And that means we have the differential of y. We want an integral of y values. We need a y interval, and the interval will come from the intersection of the 2 curves. So here let's find the intersection. Y squared minus 2 equals negative y squared, and add, or we could just, let's just add y, so that's 2y squared, subtract 2, divide by 2, and we get positive or negative 1. So the interval is from negative 1 to 1. The integral is from negative 1 to 1. Right minus left. So the right side is the negative y squared. The left side is y squared minus 2. So we have negative 2y squared plus 2 negative 2y cubed over 3 plus 2y substitute a 1. So 1 cubed is 1 plus 2 times 1. And then we'll put a negative 1 in there, and negative 1 cubed is negative 1, so that'll be a negative times negative is positive 2/3. Put a negative there and we get negative 2. So 4 minus 4/3 gives us 8/3. Alright, so this horizontal parabola shifted to the right 3. And here we have a linear equation. The y-intercept is 0 with a slope of 1/2. Up 1/2. So looking at this, at one point we'll have to use a vertical rectangle with the same curve. So here it'd be easier to use a horizontal rectangle. And that means we need y values. We need a y interval. The y interval is going to go from 3 to the intersection. So let's find that intersection. We'll have 2y equals x. So we need to solve for x and set these equal. And then we'll have 2y equals, instead of an x, let's put negative y squared plus 3. And we can move everything over. We'll have y squared plus 2y plus negative 3. We can factor that. Okay, and when I described the interval, I said we needed values from here to here, and that was incorrect. We need values from this intersection down to that intersection. We need y values. We need a y interval. We don't need the x values or the x interval of the region. So we found y values that are going from negative 3, that will be an intersection with a y value of negative 3, and here this intersects at 1. And now we integrate from negative 3 to 1, and that's going to be right minus left. The right side is negative y squared plus 3. The left side is 2y. So, antiderivative, negative y cubed over 3 plus 3y minus 2y squared over 2 substitute a 1, and we'll have negative 1/3 plus 3 times 1. Then we'll have 1 squared, 2 over 2 is 1. Let's put in a negative 3, and we'll have Negative 27 times negative 1 is positive 27. This will give us a negative 9. And here we have a positive 9 times negative 1 is negative 9. Negative 1/3, and we have 3 minus 1 minus 9 plus 9 plus 9. So here we have 9, 10, 11, 11 minus 1/3, 10 and 2/3. Alright, and we'll stop there.